This is Lab 3 for Physics 1, Black Hole. This is the table of contents I will be discussing. Firstly, what are the goals and purpose of this lab? Utilizing a computer model that replicates the gravitational interaction between a black hole and a star of unknown mass and determining the black hole's mass, and using a comparable computational model to determine the initial velocity required for a spaceship to travel near a black hole before leaving the black hole planet system, avoiding the ship entering the black hole or colliding with the planet. The free body diagram for Model 1 and Model 2. In Model 1, the system is the star and the surroundings is the black hole and space. In Model 2, the systems is the star and the planet, and the surrounding is black hole and space. For principles and formulas used, we used Newton's second law, which states that the net force acting on a system is equal to the product of the acceleration and the mass as long as the mass is unchanged. The following formulas will be used, which are the velocity update and position update formula. Gravitational force is the attractive force that two masses exert on each other due to their mass. It's one of the four fundamental forces of nature and plays a significant role in the motion of celestial bodies. Every object with mass experiences a gravitational pull towards every other object with mass. This force is what keeps planets in orbit around the sun, the moons orbiting planets, and objects grounded on Earth. Gravitational force can be calculated by the formula minus g m1 m2 over r squared times r hat. When it comes to net force, we have the parallel component and the perpendicular component. F net is equal to the parallel component plus the perpendicular component. The parallel component of the force can be calculated by doing the change in momentum with the parallel component, and the perpendicular can be calculated by doing the change in momentum with the perpendicular component. The parallel versus perpendicular component. For computational model 1, using the starter code, we're setting the initial conditions. The mass is 2 times 10 to the power of 30 kilograms, and the time interval is 24 times 3,600 seconds. This can be seen with the code to the right. And the seed is my Georgia Tech email. For the iteration, a loop should be created inside in which we declare the formulas and fundamental principles discussed in the prior slides. This code can be seen to the left. And finally, we set the final conditions to determine the mass. Here, I experimented a bit and tweaked the arrow scale, and I thought the best result was when it was at 1 times 10 to the power of minus 19. This is the result of my code, which gave me a mass of 1.85061 times 10 to the power of 34 kilograms. Conclusions for Model 1. The star's orbit is elliptical because of gravity. The net force is the gravitational force. When the star is farther away from the black hole, the net force is smaller, and vice versa. This is seen by the arrows, which differ in size between the parallel and perpendicular components. Errors may result due to the rounding of variables, and it should be noted that the parallel component represents the change in speed, and the perpendicular component indicates change in direction. For computational Model 2, we are setting the initial conditions using the data from Model 1. The maximum time will be 60 times 60 times 700 seconds, and the code can be seen to the right. For the iteration, again, we create a loop inside in which we declare the formulas and fundamental principles discussed in the prior slides, repeating the same process for the spaceship and the planet. As a result of the code, I got that the initial velocity of the spaceship is minus 4.8 times 10 to the power of 7, 2.5 times 10 to the power of 60 meters per second. The shortest distance between the spaceship and the black hole is 2.4 times 10 to the power of 8 meters. The conclusions for Model 2, the initial velocity suggests the spaceship is traveling leftward and upward. This is because the spaceship moves more to the left along the x-axis and upward because the x-component of the velocity is much larger than the y-component. At its closest approach, the aphelion, the spaceship experiences the strongest gravitational pull from the black hole. The spaceship is propelled out of the black hole planet system by the black hole's gravitational pull. As it gets closer to the black hole, the gravitational pull accelerates it, and this velocity eventually exceeds the escape velocity, enabling the spaceship to exit the system. What does this mean? How do the net force and its parallel and perpendicular components differ from the rate of change of momentum? The net force corresponds to the change of the momentum as shown below. The parallel and perpendicular components of the net force are also equal to the rate of change in momentum for each direction. When we ask what if, what initial velocity would your spaceship need to achieve in order to enter the orbit around the black hole. Compared to the initial velocity from part 2, the velocity required should have a smaller magnitude in the x component and a larger magnitude in the y component. It would result in an initial trajectory that is more vertical. The spaceship velocity would be minus 1.7 times 10^6, 1.3 times 10^7, and 0